The following is intended to give you a taster of what the professional learning will be for Unit 2 Maths. That's the applied maths, statistics and vectors. I've chosen to look at two topics, Poisson distributions and vectors, but it won't be a very long look because neither of them demand a huge amount of effort and time. So starting off with the Poisson distribution, and everybody knows that Poisson is the French for fish, but of course the Poisson distribution has got nothing at all to do with fish. Named after a French mathematician, Simeon Denis Poisson, in fact Baron Simeon Denis Poisson, has nothing to do with fish. So it's a discrete probability distribution, discrete insofar as it only takes certain values, and typically those values are the natural numbers, the counting numbers, because it actually counts events that occur. You can't have 1.8 events occurring, and these events will occur in a fixed time interval at a constant rate, and they must be independent of any other event. So typical notation, discrete random variable, frequently we'll use for any random variable, whether it's a discrete or continuous random variable, we'll use the x, and if this is a Poisson distribution with a constant rate of lambda, then the probability that x takes a particular value is given by lambda to the k e to the minus lambda over k factorial. And you'll see various versions of this, but it is one thing that students will need to know, and it's one thing they need to demonstrate. E, of course, is Euler's constant, 2.71 Planck. Another irrational number, very useful one, and it might be useful if the students already have met and know about the exponential function, which of course is in Unit 1 at 2.1.6, and it's not a bad idea. The ideal situation would be to have one person teaching Units 1 and 2, and that way you can link the two together. But if in your school there are different people teaching the pure maths and the applied maths, which is entirely possible, then it's a good idea to liaise with your other colleague to ensure that your teaching meshes together better. So it's worth noting, and the student should always note, that for a Poisson distribution, the expected value, the mean of that distribution, is equal to the variance of that distribution, and they're both equal to that parameter lambda, the constant rate at which things occur. So it's a very elegant distribution, and this topic's been around for a long time, so if you follow that link, it'll take you to mathematic.com, courtesy of my colleague at Ysgol y Croedden in North Wales, and what he's done is collected all the S1 questions from 2005 to 2019, I think, on Poisson distributions. So Gareth's done a lot of us have a huge favour there, and the questions are available in both Gymraeg and Saesneg, in Welsh and English, so it's enormously useful. And the students should develop an understanding of using a calculator to find the relevant probabilities and the tables, because whilst the calculator is a great device, and I'll show you how to use a calculator, then some questions cannot be done on a calculator. You will need a set of tables for them, but they are relatively straightforward if you do some thinking. So I would suggest that your students, because they're mathematically able and technologically able, actually have a copy of these tables on their laptop or smartphone. They don't take up that much space to be able to review them as and when they need. Of course, the other thing you can do is go and get the copies from the exams officer and photocopy them. So I'm using a question just to demonstrate the sort of thing that we want, and this is from the old S1 Statistics 1 2016 question 5, and I am only dealing with the English medium question. If you want the Welsh medium question, then it's dead easy to do. Just replace my question with the Welsh version. So I'm told in my question it's a Poisson distribution. I'm told that the mean E of x is 0.25t, where t is the number of minutes that the time interval is of duration. So without using tables, and this is a fairly typical sort of question, without using tables, determine the probability of the number of arrivals between 10 and 10:30, i.e. t is 30, is exactly 5, or more than 5. And then the second part is the bit where you'll have to use the tables because that calculator cannot do this particular thing. I suppose you could do by trial and error, but it would take you one hell of a long time. So it's probably not a wise move. And this is worth 9 marks. It's nice and easy. It's a sort of question, and the questions don't change that much over time. These are the sorts of questions you would expect to meet on the Unit 2 paper without any real problem. So I'll address A1 first of all, the probability that x is exactly equal to 5, so probability x equals 5. So I would, in a question like this, always start with the fact that they give me a mean of 0.2t. So my lambda, and I'm using lambda, I'll talk about later on, WJC tend to use m, but that's their choice. So lambda is 0.2t, t is 30 from the question, so therefore 0.2 times 30 will give me 6. So I'm stating that x is a Poisson distribution. Now you can either use PO for Poisson or P. I don't use P because of course then there's a probability, confusion with probability, with parameter 6. So it's a Poisson distribution, parameter 6. And I know, and you know, that the calculators, the trusty class whiz 991EXs, will do this particular sum for us. But if it's an exam question, you've got to show that you're doing the piece of work. So therefore, whilst it's not necessary to state that the probability x equals 5, or x equals some constant is equal to the lambda as the constant e to the minus lambda over the constant factorial, it is worthwhile showing that you understand exactly what it is. So with lambda equal to 6, the probability x equals 5 will be 6 to the 5 e to the minus 6 over 5 factorial. And that's a straightforward calculator piece of work. Pressing the buttons on my calculator in that format, come to that in virtually any other order will do it, will give me 0.160623141. Part of the issue with that is over specification, probabilities. I know some examiners, especially the board I'm marked for, if you'd left that as an answer, you would lose marks because it is over specified, it is too accurate. So therefore it's not unusual to round probabilities to a reasonable degree of accuracy. 0.1606, you might even get away with 0.16. approximately 1/6. So fairly straightforward, but I would expect to see that as a minimum amount of work for my first part, Roman 1. Now, using my trusty calculator, and this is a screenshot from the emulator, and it's worth, if you're teaching A-level mathematics, getting hold of the Casio emulator, because you can then project your calculations onto the board. And the bottom box is a keylog, so it's what I've actually had to press in order to get from my normal calculation mode. So menu 7 is the statistical thing, down arrow because the up arrow gives me other distributions. I select the one I want by 2, it then offers me list or variable, and I want to actually go with variable 2. It asks me what my x value is, 5, press the equals to input that. Then asks me my value for my lambda, and the reason I use lambda is because that's what the calculator uses, equals 6, press the equals to put that number in, and then press the equals again to reduce this p equals, and you can see it's exactly the same to as many places of decimals as this display will allow me. So that calculator will do it, but they've got to have some writing. There's no point in just writing these things down, because if you've made a slip on one of the numbers, you will get no marks. Whereas if you've shown you're using the formula correctly, even if you've got the wrong number, let's say for example, for some obscure reason 0.2 times 30 didn't come out to be 6, you'd still get the method mark. You wouldn't get the accuracy mark, however. So we know that total probability is equal to 1. It's something we've been telling our students for a long time. So our probability scale always works from 0 to 1. And the probability that x is greater than 3 is fine, but that means I've got to calculate the probability that 3, 4, 5, 6, 7, 8, etc., 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 etc. ad nauseum. So that is too long a task. And so what we would tend to do is treat this as 1 minus the probability that x is less than or equal to 3. Notice these strict inequalities here. So I'm interested in the probability that x is greater than 3, and this is a very definite RTQ, read the question point. You know, how strict are your inequalities? And you must be strict on the inequalities in these sorts of questions, because otherwise you'll get a completely different answer. So the probability I'm asked to find is the probability x is greater than 3, and the way I'll go about that is 1 minus the probability x is less than or equal to 3, and my parameter is still 6, because I'm still in the same 30-minute time frame. So the probability x is less than or equal to 3 is the probability x is 0, 1, 2, or 3, and because they're reasonable probabilities, I can add them together, not a problem at all. So plugging each one into my trusty formula, you'll see that e to the minus 6, 6 to the 0 is 0 factorial. Of course, 0 factorial must be 1, otherwise our number system doesn't work the way we want it to do. Plus e to the minus 6 over 6 to the 1 over 1 factorial, etc., etc., etc. So, and it's not a bad idea if students are using calculators to take that e to the minus 6 out. And of course I've put 6 to the 0, which is 1 over 1, hence 1. 6 to the 1 over 1, hence 6. 6 squared is 36, 2 factorial is 2, hence the 18. 6 to the 3 over 3 factorial. 3 factorial is 6, so it's the same as 6 squared, 36. Which will give me 61 e to the 6, and you really needn't write these two lines in, but it's a good way of showing it, and that gives me a 0.1512, again over specified, etc., etc. So the probability that x is greater than 3 is going to be 1 minus that particular result, which rounds to 0.8488 to 4 decimal places. So I've dropped out the display screen bit, so again this is another screenshot. So again, if I've been using my calculator for something else, menu 7 takes me to the statistical distributions. I've got cumulative and such other things as well, but we won't talk about those. We can explore the calculator in more depth later on. Okay, so downward arrow. I want a cumulative, so instead of selecting 2 as I did before, in other words, I don't want a specific value, I want a range. Gives me 3. 2, I'm on variables. Now, as it happens, because I'd used this calculator before, No, it does. Okay, x is 3, so it's less than or equal to 3. And notice that inequality coming in. Press the equals to put that in. Put my parameter in 6. Press the equals again. And again, I get exactly the same answer on my calculator as I did by my 61e to the minus 6 bit. Now, you can on your calculators, by going menu 1, which takes you back to the normal number sums, because it will store that 15120388828 in the register. I can do 1 minus the answer, and it will give me this 0.848796, which gives me my 0.8488 to 4 decimal places. So that calculator is a very useful thing. That Casio emulator is free for the first 90 days and costs you £11.34 a year after that, which I think is money well spent. So looking at the tables give me probabilities, random variable x with a mean m. Notice that WJC use m less than or equal to, so the tables are cumulative. So from my question I know that t is unknown but less than 30, and I must point out that the tables give cumulative probabilities. They don't give point probabilities, they just give cumulative probabilities. So they use, as I've said already, m instead of lambda. So the probability that x is equal to 5, which is what I'm trying to find, is the difference between the probability that x is less than or equal to 5 and the probability that x is less than or equal to 4. So looking at my book of tables, and I'm not going to project the whole set of tables into this, looking at my set of tables, I'm discarding the first section of the tables because the differences between the probabilities I'm looking at, 5 and 4, are too small, way too small. They don't come anywhere near the value I want. So I'm looking at the second set of tables where this is the parameter between 2 and 5.5. My x values down the side there, and I'm looking at the 4 and 5 lines and just scanning across. I'm looking for two that give me that difference of 0.0602, which I'm looking for. And you can see quite quickly, when you know what you're looking for, and I suppose that's where experience comes, that relates to an m of 2.4. And this is just an extraction from the WJC elementary stats tables. So m is 2.4. My probability that x is less than or equal to 5 is 0.9643. M is less than or equal to 4, 9041, and the difference between those is the required number that I'm looking for, 0.0602. So therefore the implication is that m is 2.4, but of course m is 0.2t, or lambda equals 0.2t in my normal notation. So it follows that t must be 2.4 divided by 0.2, and my time is 12 minutes. So I could get that using the calculator, but it would take me a lot of button pressing, a lot of trial and error, which is not great. So Poisson distribution is not too difficult. If I move on then to Newton's second law and a bit of vector work, and these are much loved topics. So Newton's second law, force equals mass times acceleration. The greater the force, the greater the acceleration, providing your mass stays the same, and vice versa. It's a straightforward, direct relationship. So it's a simple enough 3-variable function, and you will see it in exam questions where you're given 2 of the variables and asked to find the third. Not a difficult piece of mathematics, straightforward, simple, easy peasy. The one issue with this is that they love giving you the forces in vector form, and most of our students, because vectors aren't really included in GCSE anymore, they were taken out of the syllabus a number of years ago, have little or no experience in vectors. And Unit 1 will cover vectors, but again it comes back to the stage of, ideally if you're teaching it yourself, both Units 1 and Unit 2, you can link the two pieces of work together. If not, you need to liaise with your colleague. So it's useful if the students are aware of vectors, and neither of the units require much in the way of vectors. But it's not unusual if you look at the specification. Vectors are 2.1.9, and as a consequence, they can be left until very, very late on and given a very cursory glance. But students need to be confident at using it if they're going to get anywhere with them. So I would suggest that it's worth looking at a little bit of work on vectors, and if you pre-teach what your colleague in pure maths is going to do, then comme ci, comme ça. So you want to be looking at length of length. Obviously they need to know that a vector is something that's got magnitude and direction. They need to be able to find both the magnitude and the direction. But these are not difficult tasks, but given that we're in a two-dimensional framework, straightforward Pythagoras and straightforward right-angle trigonometry will give you both magnitude and direction, easy peasy. So again, I'm using an exam question, this from the 2019 paper, question 6, and I've got my three forces. Now, I personally don't write my vectors in I and J notation. I always write them as column vectors. So my first form in my case would be 6 minus 7 as a column vector, column pair of brackets, and you'll see me write that in a second, etc., etc. Now, this whole question relies on nothing more than vector addition and vector multiplication by a scalar. So relatively easy. It's intuitive, I think, but worth pointing out that vector addition, simple, straightforward. Might be worth showing a GeoGebra app at this stage, or demonstrating in graph form. But you simply add the x components together and the y components together, or the i's and the j's, whichever you prefer to do. I and j, of course, standard notation for unit vectors in the x direction and the y direction, and k and the z when we come into 3 dimensions, but not at this level. So I would personally say that for every mechanics question, draw a diagram. It's one of the things that my colleagues and myself bang on about all the time. So my diagram's fairly rudimentary. I've got my object of mass 2. You notice my three forces, I've used different colours. So my light blue force, the 6 minus 7, goes across 6 and down 7-ish. I don't know where the A one, I don't know how big A is, so I've just drawn it some length, A2. And my third force, F3, which is the 5i plus bj, I've just written as 5b, and I don't know whether it's going up or down. Doesn't really matter. I've just got this sense that they're all going in the same direction. Notice they've got to have a magnitude, so relatively easy, but I don't need that particular piece of information in this question. So, and the other thing I've got is that my acceleration is in the form 7 minus 3. So therefore I can tell that it's going to, I can tell that I've got them in roughly the right sort of directions. So simple addition will do the job for me. My first part, if I add my components together, 6 plus a plus 5 gives me 11 plus a, minus 7 plus 2 plus b gives me minus 5 plus b, or b minus 5 if you prefer, it doesn't make any difference. And now I can use my Newton's second law, force equals mass times acceleration, so therefore it follows that my overall resultant force, the 11 plus a, minus 5 plus b, is equal to the mass, which was 2, multiplied by the 7 minus 3, which is the acceleration vector, And multiplication by a scalar is simply the same as addition of the same thing twice. So 7, 3 added to 7, 3 would give me 14 minus 6. So therefore multiplication by a scalar, 2 times 7, 2 times minus 3, it's distributive. So therefore I've got that 11 plus a is equal to 14, and minus 5b plus minus 5 plus b is equal to minus 6. So it follows reasonably logically that a has got to be equal to 3 and b is equal to minus 1. Very simple piece of maths, but worth marks in these questions. Easy peasy. So constant velocity. Now this is where you've got to read the question. So the second part told me that it was travelling with constant velocity, which implies the acceleration must be 0, because if the acceleration was positive, it would be accelerating, it would be speeding up, and if the acceleration was negative, it would be decelerating, it would be slowing down. So therefore the implication is constant velocity is that acceleration equals to 0. Draw a diagram. I know that I've got my mass of 2 still. I've got an acceleration. You notice I put a double arrow on there to show that my acceleration is equal to 0, but I've simply shown a direction to it. And the minus 14 minus 6, sorry, the 14 minus 6 is my overall vector force in that particular case, because if the x direction is 11 plus a, where a is 3, hence the 14, minus 5 minus 1 is my minus 6. And it's roughly the same direction. These are never to scale. Let me say I can't even draw straight lines, so they'll never be to scale. And in order for my acceleration to be 0, the force has got to be equal and opposite, which is another Newton's law. So if a equals 0, the forces must cancel each other out, so therefore the summation of my forces must be equal to 0, 0. It's fairly obvious, and you don't even need to put that line in there, that my F4 must be minus 14, 6.